If you have questions, you can interrupt me and it is fine. And I will not read the chat. So I will talk about the Gusarov-Polyakh-Virov theorem, or for short, just GPV. Okay, so approximately what the theorem is saying is, if we have a finite type invariant, we can compute it on a diagram by looking at the subdiagrams with less than or equal to n crossings, where n is the degree of the invariant. So just to recall, the finite type invariant, it's a map from usual knot diagrams to some abelian group. And if we let this double point denote, with arrows, some difference in these crossings, then V on a diagram with greater than n double points and possibly other real crossings where n is this degree should be 0. So this is finite type invariant. And then by subdiagram, what I mean is if we have a diagram, so not diagram, a good place to mention is now, I guess, that when I say knot or knot diagram, I mean long knot or long knot diagram. So everything is like a line and then knotted and then continue. So we have a knot diagram. And
Jessica, I have a quick question.
Yeah.
Sorry, so for the long knot, am I imagining like the line continues to infinity, or just stops at a point on either side, or maybe does it not matter?
I think it doesn't matter. Infinity is good.
Okay, so these are just lines just going out forever in either way.
Yeah.
Okay, cool.
So instead of thinking of it as this nice picture, we can isolate the crossings and just think of this diagram as a collection of crossings. So this crossing here would be like this. We can think of it as a collection of crossings with labels that indicate how they go together. So here, this attaches here, so we can call this A, and A attaches to A. And then we have B, which attaches to B, and C, this comes over here to C, over here to C, D, this, and E. So we can think of this diagram as this collection of crossing labels, and here is the start, and here is the end. So if we can consider it as a collection of crossings, we can consider any collection of crossings. In particular, we can consider sub-collections. So if we consider maybe this sub-collection of crossings, we can look at it like this. And I'm redrawing them because we want to relabel them, because the labels don't match up now. So A, if we look on our original, A is here and it comes and connects to B. So I'm going to change the B label to A, and C is still to C, and D now attaches to E. So I'll call this D. So this is a sub diagram. And we can try to draw the sub diagram as back into like this form. So we'll try to draw it.
Wait, Jessica, another quick question. Sorry. So you changed the labels when you made the subdiagram, so you sort of forgot that you passed through the middle crossing or something? Is that what you did?
Yeah.
So you just followed A, and then A attaches to B, so you just said forget the fact that we called it E, you just call it A still?
Yes.
Is that okay? Okay.
Yeah.
Thanks.
Yeah. So we just draw it like this, and A, we draw this crossing. It's good. It attaches to A over here. I'm rotating this second one now. So we're virtualizing it, but we can not call it that as well, and we are still happy. So we connect, and we want to draw it. So we connect C, but now if we want to connect D to D, we have to create a new crossing, but we don't want to do that because we wanted our subdiagram to only have these two. So we go through like this, and we don't want this to be a real crossing. We want this to be a virtual crossing. Like, we will call it a virtual crossing. And it's the same as just looking at this diagram and just like drawing it in. Yeah, and we'll call this kind of knot a virtual knot. And we'll consider normal knots virtual knots as well. They just don't have any virtual crossings, or we can create a virtual crossing on them. It's fine. And we'll denote the set of virtual knots by virtual knot, I mean virtual diagram. Yeah, we'll denote it by VD as opposed to UD, so V for virtual. And I didn't say this before, but of course we want the finite type invariant. I made it a map from diagram, but we do want it to be a map from knots, so we want it to respect Reidemeister moves and like moving around. Okay, so the same, this is the statement informally, but the statement more formally of the theorem is if we have a finite type invariant, this is our finite type invariant, and it has degree n, then there exists this W over here so that we can factor in the following way. So that we can, if we want to compute V on a diagram, we can first compute S. So S is a map that takes the diagram to the sum of all subdiagrams. The sum of subdiagrams. And then apply W to compute V. And then W should also vanish on diagrams with greater than n crossings. So we can also first do S, get rid of the ones that have greater than n crossings, and then apply W. And I wrote this triangle part down here to remind us that V is an invariant of knots. It's not just a map from diagrams, but we can need to write it. And so this is good, like we can compute it, with the n fingers, we can computing the subdiagrams, but another good use for this theorem is because W is just a map, a linear map that vanishes on diagrams greater than n crossings, and there's a finite number of diagrams with fewer than n crossings, we can find all the W for some n, all possible W for some n, and that will help us to find the possible V for this n.
Just to clarify, conversation that's happening in the chat about if W is unique, and drawer answered no. I would have thought it was unique. So W is not unique?
It is not certainly unique. It is not. I'll explain it in a bit.
Oh, okay, so there are other W's that would work.
Yes.
Weird. Okay, cool.
Oh, actually, okay, I'm not sure. I'm not sure if there are other ones that work, but I'm also not sure if it's unique. Anyways, so to prove this theorem, we want to construct.
I just lost my confidence, so I'm not sure it's unique either. Okay. I'm pretty sure it isn't, but I can't right now write a counterexample. So.
Yeah, okay. So we want to find this W. And the first thing is we want this triangle to commute. So it would be nice to define W in a way that just makes it commute. So if we could somehow define W to be like some kind of S inverse, and then V, it would just define it this way, it would be great. So let's talk about S inverse. So S is the map that takes the diagram to the sum of subdiagrams, and we can think of this as a +1 map, where in the following way. So if we pick some particular crossing X, then, and X is like in D, then the sum of all subdiagrams of D is the sum of the subdiagrams that contain X. So this is the subdiagrams containing X, and the subdiagrams that don't. So if we just let X, represent this crossing, Y represent this crossing, then we take the sum of the subdiagrams, we can write out the terms like this, and so on. And this is just the same as if we did like the +1 first. So like it's the same as doing like the +1 independently to each crossing. So S is just like the +1 map. So then the inverse should be the -1 map, which is just taking the sum over all subdiagrams again, but then with this extra sign. And the sign is the difference in the number of crossings. So this is the number of crossings in D, but not the subdiagram D prime. So then, so the example here, I feel like this is just one term. So this term is like where this one term would go after applying, we apply S, and then this one term we apply S inverse, and then we would get this whole thing. And if you're not convinced by this +1 -1 thing, you can think of it as like after we apply to each of the, we apply S inverse to each of these terms, and like the minus, the diagrams with the minus, they will, like everything will just cancel out, we'll just be left with this. Okay, so we have this S inverse, so things are looking good for us perhaps.
Okay, I have another question. Sorry.
Yeah.
Full of questions. Okay, this map S, so we're computing an inverse. Are these sort of, I don't know what the right word is. Does this show that S is some type of like isomorphism? Or like, is there any sort of like algebraic structure that's being preserved or something? Or is this just like a set map and then there's this type of reversal inverse map?
So
does that question make sense?
I think so. But we can consider S to be an isomorphism but it's kind of lame because our space is just like formal linear combinations of diagrams. So then we just define S so that it, like S on the sum is just S on each term. So it's like linear, and there's a bijection. So I guess it's like a linear map. It's an isomorphism between like C modules, but yeah, I'm not sure if that helped. Okay. Yeah, okay. So we have so we have S and we have S inverse. So going back, so going back here, maybe life is good because we have this S inverse, so we would like to just apply V and be done with it, but we have a problem because to apply V, we need S inverse to land in this space of usual diagrams or diagrams that represent real knots. And we can see that S inverse, like for example, these terms like this, okay, maybe it will be a real knot, but it's not clear that like the image of S inverse is not going to be only diagrams that represent real knots. So our problem is that S inverse lands in virtual diagrams instead of real diagrams. But that's okay. We are optimistic and we think maybe we can just fix this by projecting down into the space of real diagrams. So if we can find a map P that associates virtual diagrams to real diagrams, then maybe we can still just define W to be this composition and maybe everything will still be okay. So we needed this lower triangle to commute, so we needed going S and then W, which is S inverse PV, to be the same as going just V. So that's the first condition, to make sure everything commutes. By everything, I mean this lower triangle. And then the second condition is just what we wanted. We just wanted W to vanish on diagrams greater than n crossings. And an irrelevant aside is the letters I'm using here are the letters from the letters for the maths are the letters for. Sorry, Zoom is giving me like a notification for some reason. Are the letters from the original paper, and they kind of make sense, like S for sum, P for projection, W because it's close to V. But if we change S, instead of calling it S and we call it G, then we can call this GPV, and that's kind of cute. But that's not relevant. Okay. So then we can define, so if we find this P, then we can define W, and everything should be good. So our next step
question. Sorry.
Yeah.
Question. Okay. First of all, I love your GPV. That was awesome. Okay. So going back to the uniqueness question that was coming up. So if this is indeed true, we're defining W to be, GPV. So is that saying that for a given V, it uniquely determines W? But like if you could give me a different V, there's going to be a different W that works. But like,
so a different V is definitely a different W.
Okay. Different V is a different W. Okay.
Yeah, the thing that I guess I'm not sure about is if for every V there is one unique W or many Ws. And I guess that this is related also to the next point where we're going to define this P.
Sorry, just one word, Nancy. So P is not unique. So, I mean, if given, once you fix P, V determines W, but P is not unique.
Okay, so the S is unique, right? Or the statement of the problem is like, given this S, using this S, then there's this linear functional that like works with it.
No,
yeah, not changing it.
Sorry, I shouldn't. Jessica, you should answer. Sorry.
No, I don't know if I have a good answer. Like S is like the top half of S doesn't matter. Like we just want to look at the subdiagrams with fewer than n crossings, and S is like a convenient way, I guess, for us to just consider all of the subdiagrams that have fewer than n crossings.
Okay, thank you.
Yeah. So we want to find this P, and this talk about P being unique or whatever is great because this is kind of my next point. So first we will define P, but I put quotes around what P is because this is only one version of what P can be. So in the original paper, they present some P, like they present some math, but it's, in my opinion, like a little bit difficult to follow. Like they're doing it in terms of Gauss diagrams. It's not very clear what's going on in the diagram. So then some other former student of drawers, Shionten Rukema, rewrote this and like introduced trees and made everything more like visual. But unfortunately, so I was going to present that version, but unfortunately I do not understand the proof of that version. And I thought I did until yesterday at like 3 p.m. But now I don't understand it. But so now this is what I'm presenting is like some combination of these two things. So this is why what P is. Yeah. Okay, so onto what P is. The first thing we're going to do, like the first thing that P is going to do is we're going to make a first come first served tree. So what that means, tree meaning like a graph theory tree, where the vertices are the crossings and the edges are just the strands between the crossings. And the vertices come with all the information on the crossings. And first come first serve just means that the crossings that come first, we draw them in first. And we want it to be a tree, so at a point we're going to connect a strand that's going to not make it a tree anymore, we just don't connect. So an example maybe. So if you give me maybe this, we can consider double points because they will just be, we're just viewing them as like linear differences of regular crossings. Okay, so suppose you give me this collection of crossings in here. Then I will try to make a tree. So this is the start. So I will draw this crossing. Everything is fine. And then we continue. So we just continue along this path. We draw the next crossing. Everything is fine. And now we want to connect B to B, but this would make a loop and this would not be a tree anymore. So we just don't connect, but we just keep going. So we keep going down like this. And then C connects down here. Oops, made this a little long. And then D here, we don't connect, but we keep going. And E is here, we don't connect, and we keep going, and we are done. So this is our tree. I guess I don't have to draw this long like this. Okay, so the first step of P is we make this tree. And then I will copy paste this. I will copy this so we can keep using it on the next page. The next thing we do is we are going to change all bad crossings to good crossings. So a bad crossing is just a crossing where the under strand comes first. And the good crossing is just a crossing where the over strand came first. And we just decided which ones were good kind of randomly. We could have swapped them, it's fine as well. And so in this here, like we are coming over. So this is a good crossing. So we're going over first, and then we're coming here, and then we come here, and now we're going under first. So this is a bad crossing. So we would change this tree into two trees, and one of them would have this crossing being replaced by this, and the other tree would have this crossing replaced by this, and there would be some signs. Okay, so we do this, we change all the bad crossings to good crossings.
Jessica, question.
Mm-hmm.
So I'm a little confused. So when you went down to the crossing you said was bad, it was bad because it was an under crossing, like the strand went under? Can you explain? Can you maybe explain why it was a bad crossing again? I didn't quite.
Yeah,
follow.
I think by bad crossing I mean if we are just going along the knot in the natural direction of the knot, then we're meeting the crossing by going under first. So the first time if we go along here, the first time we're entering this crossing, we're going like on top, so it's fine. So this one is good. But then the first time we're meeting this crossing, we're going under first. So then it's bad.
Okay, so you're going along, there's like a parameterization of the knot. So you're going along the parameterization and you want every time you reach a crossing, the first time to be an over crossing.
Yes.
Okay.
Yes,
okay.
exactly.
Okay.
Yeah. It's first meaning in the order that we're going in the knot. So this is fine. We change everything to be good. The next step is a little complicated. So it's to sweep the first real crossing on the double point tree. So there's lots of words here. So there is sweep, and there is first, and there is double point tree. Wait. So double point tree. We have a tree, and the double point tree is the smallest subtree containing all double points. And we also want it to contain the root of the tree, so meaning the starting point. And we also want this tree the subtree to actually be like representing a knot diagram. So like all vertices should either be crossing their endpoints, so all vertices should have degree 1 or 4. So for example, this is our tree. Then the double point tree would have to include all the double points. And then it would have to contain the root, and it would have to be a subtree, so it has to contain all these in between. And because all vertices, like we actually want vertices to be crossings, we need to include this part, and we need to include these two, and we need to include this one. So this would be our double point tree. And the real crossings on the double point tree would be like these two, because these are the non-double point crossings. What do I mean by sweep? Sweep, okay, so sweep is if we have a real crossing and a double point. To sweep means to pull the real crossing through the double point, so like this. So instead of going like that, we now come across like this. And we still want it to be a tree, so I mean, I guess this part is maybe not so important, but we can also, if we want to think of it like a tree, it's like this. We just cut here. Okay, so sweep, and I want to sweep in the direction of the leaves. We want to like continue along the strand, and we want to sweep in the direction of the leaves of the tree, so away from the root. And then finally, what I mean by first is we're just going to put an ordering on all the real crossings. So first, we're just going to order by distance from the root. So if they're closer to the root, we sweep them first, and maybe then like counterclockwise or something. So we're just choosing ordering. So we can see like in P we're making lots of choices, and this is kind of why P is not unique, because we can choose to do these in many different ways. Okay. So the next step is easy, because the next step
Jessica, sorry to interrupt. In the diagram that you showed in the last example, I'm just wondering why the so on the longest strand, the third point from the left, the one where we take the one after that, where we, yeah, I'm just wondering why that one we don't need to also include the two other edges connect to it, since at this point it's degree 2.
Yeah, that's a great question. I just forgot to draw them. You're right. Yeah, they should. Yeah, okay. They should have these. Yeah. Yeah. Okay. So the next step is easy, because the next step we're just repeating what we already do, like what we've already been doing. We want to repeat step 1, 2, and 3. So repeating step 1 means like after sweeping, we've replaced this with, we've swept, and this tree, it's still a tree, but it might not be a first come first serve tree, meaning, of these 3 crossings, maybe the tree is not drawn in a way such that if you gave me all the crossings and I tried to draw them first come first serve, it might be different. So we're going to reconstruct the tree into a first come first serve tree, and then we're going to change all the bad crossings to good crossings, and then we're going to sweep again. And we're just going to keep doing this over and over again until one of two things happen. So until all terms satisfy one of the following. So either they have greater than n double points, or we don't, all terms are so that we don't need to do 2 or 3 anymore. Meaning there's no more bad crossings and there's no more real crossings on the double point tree. So we just keep doing this until all terms satisfy this.
Quick question. So I'm a little bit confused about how to repeat step 1. So step 1 was when I had a diagram. So I just had a list of crossings and connection rules. And then I start at the start and then just first come, first serve build. Okay, then you're saying do all this sweeping and stuff, take a double point tree. What have we changed so that, what have we changed so that if I were to deconstruct it again as a diagram and then try to do it again, I don't understand what is going to be different.
Yeah, that's a great question. Well, I will maybe do the example here and then it will be more clear. So suppose we swept this first real crossing, so now it becomes like this. Then we can notice of these 3 crossings, one of the ones on the side, pretend this crossing would not be here because this crossing, perhaps, okay, sorry, if this end was attached to this end, suppose, then previously we would have had to not draw on this edge. Previously we would have had to not draw on this edge and just come in here. But now this crossing, we could just draw this crossing over here instead. This crossing would be it would first appear over here rather than randomly on this branch.
So the first come, first serve bit, what's changing is our ability to reconnect backwards or not. And so by kind of reconfiguring the crossings, that's going to change when we're allowed to connect up or something. Does that make sense?
Yes. It's we're, it's we've chosen to not reconnect backwards when we could have still reconnected here. Yeah.
Okay.
Yes, so we're just going to move everything. Yeah,
so
that it's still.
So when I have this tree, then I'm just I decompose it again into just a bunch of crossings with connection labelings and then start over. Is that the idea?
Yeah, that would be okay. But I think the only things that will be affected are the ones that we've changed. So we only actually have to look at those and whatever is coming off of them. We can just
Okay, cool. Thank you.
Yeah. So onto this repeating. So we repeat it and we remake the tree and we do all this. And so to make sure this step 4 is actually good, we need to make sure that this will actually terminate. And it will because here when we're doing the sweeping, if we sweep enough times, eventually the branch that we are sweeping will become clean. So if we sweep enough times, we've created a new clean branch on the double point tree. And then recreating the first come first serve tree, it only affects it really only affects the ones it does not affect the parts that are good. It does not affect the double point parts that are already good. So recreating the tree does not it only shuffles around how these branches are. So if we sweep enough times, we clear another branch. So if we sweep enough times, meaning we repeat step 3 enough times, we're going to get a huge number of clean branches on the double point tree. We will get lots clean branches on the double point tree. And if there are lots of clean branches, that must mean we have lots of double points on the double point tree and so we'll have lots of n double points. Or we don't sweep enough times, or we're not sweeping that many times because we have like finished, because there's no more step 2 or step 3 to do. Okay, so it will terminate. Then lastly, all we have to do is, if it already has greater than n double points, we will just set it to 0 because it's going to go to 0 anyways under V. We just don't care about it. And otherwise, we will just connect the strands off the tree in a good way to make a knot, meaning off the tree, meaning so that we're connecting it away from the tree so it doesn't intersect the tree. And in a good way, meaning the same meaning of good as up here, meaning like over a strand. Sorry, over crossing. Over strand. Comes first. So for example, this I'm drawing here. Oh, I didn't need to draw the A. Here, maybe we have a here, it's good. The double point tree is clean, and this crossing is good. So we would just connect. From here, we would just go along, connect, and we don't have to like erase because we're just always going over first and then under, so we don't have to erase, and I think they're good. And in this form, we can kind of connect however we want because it's very clear like which strands are going to be on top or under which strands. Like this strand comes first, so this strand will be on top of all other strands, and then this strand comes second, so it's it's second on top of all other strands. So we can like move these strands around, and they stay within their own layers, and it's all good.
One more question. Does this process yield a single diagram, or is it going to be a sum of diagrams?
Oh yeah, it's definitely like a huge sum of diagrams, especially if maybe it's not, but if there's like changing in this step, when we change the bad crossings to good crossings, if there's lots of bad crossings, then we have to replace them. Yeah, so we will, and then every time we sweep, maybe we will create more bad crossings, and so even in small examples, they kind of become a lot.
Okay, so it's the process of changing the bad crossing to the good crossing that you're introducing a sum of 2 diagrams.
Yes.
Okay, and then that just snowballs. Gotcha. Okay, cool.
Yeah. So this is P, and we're done creating P, and we just have to show that it works. So there's 2 things. So the first is to show that P does not change the value of V. So we just have to make sure that these steps don't change the value of V. So the first thing, like on real knot diagrams, because V is not defined on virtual knot diagrams. So we have a real knot diagram. I forgot to mention this earlier, but if we have a real knot diagram, then the process of making the first come first serve tree is just cutting the strand every time we're about to enter the crossing for a crossing for the second time. So along here, we go like this, first time, but now here we're going to enter this crossing for the second time, so we will cut, and then we'll keep going, and then we're going to enter for the second time, so we cut, and we keep going, and we're about to enter for the second time, so we cut. And then we cut those strands, we can unravel it, now we get a tree. So so the first thing we do is we cut, and then we change changing all bad crossings to good crossings. This does not change the value of V because we're just defining this double point to be this difference. 3, we're sweeping the real crossing under, but this also doesn't change because this is just like, this doesn't change anything because it's just like it's just Reidemeister moves to go like this to this. So just, and then step 4, recreating a new first come first serve tree, we can think of it as just rejoining the strands that we've cut and then potentially cutting elsewhere. So we're just cutting, doing some local things near the edges that don't change the value of the knot, and then rejoining. And then at the end, we rejoin, which is just rejoining the most recent cuts we've made. So yeah, so P is really not doing anything at all on real knots. Great. So now the second thing is showing that this thing is actually 0. And this is a little bit involved and kind of gross, but we'll see. So the first thing we're going to do is we're going to show that this is true on so-called good diagrams. So first, show it's true on good diagrams. And by good diagrams, what I mean is ones where we don't need to do steps 2, 3, or 4, meaning there's no bad crossings, no real crossing of the double point tree. We just make a first come first serve tree. It's a perfect tree, and then we just connect. So they're ones where we don't have to do steps 2, 3, or 4. And this might be a bit confusing because this map takes as input things from here, whereas this good thing is the thing about the map P, so this goodness is about things over here, which is the same space, but it's what we want to apply to it. So why do we want a good thing over here if the goodness of it is coming from over here? And it's because S inverse is going to preserve good diagrams. So first we want to show that S inverse, I guess it's not really correct to say want to show here. It's not like first we will show that S inverse of good diagrams will always be, it will be a sum, but it will be a sum of still good diagrams. And to show this, we first show that S inverse preserves double points in the sense of if we have a double point, then we apply S inverse, all the subdiagrams in the image will also still have that double point. And we can see it's true because S inverse of some diagram with a double point, it will be the diagrams, it will be S inverse of like this minus S inverse of that, which will be the subdiagrams with this crossing minus the subdiagrams without this crossing. And then there is some perhaps sign in front of it, minus the same thing, but with the crossing changed the other way. So the subdiagrams with this crossing minus the subdiagrams without it. But the subdiagram without the crossing that has changed, like this is just the same. So these cancel out, so we get some, there's the same sign in front. And so we get some sign times this, times like the subdiagrams with this, minus the subdiagrams that. And so this is just the double point. So so the image contains all the same double points as the original. And the same is true of S. So S and S inverse both preserve double points. So because of this, S inverse preserves the double point tree. Like if the double point tree has no real crossings on it, then the double points are kind of coming first on their with respective branches. So all the double points are still kept, so the double point tree is still preserved. So the difference between the terms and the images of S inverse are just, they have like different good crossings on like the edges near the leaves, like this. Okay, Okay, so S preserves good diagrams, and so now y is this equal to 0 on good diagrams. It's kind of easy maybe to see with an example, but the gist of it is just at the end when we connect, if there's some missing crossings, we can just connect through the crossings instead and everything will cancel. So I'll do it with a small example so we can see. We'll take the same tree that we're using before. So suppose we have this tree and it's a good tree. Oh, sorry. And it's in this space. So this tree is in this space, and we're going to apply S inverse PUV. Then when we apply S inverse, suppose it has some real crossing here, it will become like this. We will get two copies of this tree. One with the, sorry, there's a minus in between them. One of them with this crossing, and this other one will not have this crossing. So the other one will not have this crossing, and then this E will become a D because D will connect through E directly to D. And then when we come to do step 5 to do the joining, here we will get B, D, E like this. And on this one, we could go like B, D here, but instead of choosing to join D in this small little loop, we can just pretend as if this crossing that we threw away was still there and just go through here anyways, because it doesn't matter which order we, right? So these are the same. So they cancel each other out. So if there's a real crossing, the diagrams containing that real crossing will always cancel out with the diagrams that don't contain that crossing after we connect. So we can just connect through that crossing. And if there's no real crossing, so yeah, this is the case with the real crossing. If there's no real crossing, it's easy because then there's just greater than n double points, and so it just goes to 0. Everything goes to 0, and we're done. Okay. All right, so we've shown that it's 0 on good diagrams. So now for a general diagram, what we're going to do is we're going to associate a good diagram to each general diagram that has the same value of W. And the good diagram will have at least as many crossings as the perhaps not good diagram. And so that will go to 0, and so the other one will go to 0. Okay, this is maybe a bit confusing. So suppose we have a diagram, and let's call it XYZ, and it's in VD, meaning it has crossings X, crossing Y, and crossing Z, and they're connected together in some way. And suppose, let's make crossing Z a double point just so we can see, and these are just regular crossings. And suppose there is a bad crossing, and suppose X is the first, meaning in the order some order we want to choose, the first bad crossing, meaning the first, yeah. Then, and we want to compute W on X, Y, Z. Then W is linear, so we can write W X plus 1 Y, Z. So this X plus 1, it means like expand the terms and look at all those diagrams. Minus W of YZ. And then we can ignore this part for now and just look at this part. So this part is VP S inverse of X plus 1 YZ. And this is VP, and taking S inverse is like a -1, so this is X, Y minus 1, Z, because double points, remember, are not changed by S inverse. And now because x is in all this, like if we expand this out, x will be in every term. So this first bad crossing x will be in every term. So in every term, we can fix this first bad crossing. So this becomes VP, and to fix it, we're using the relation, double point relation, which is like x minus x bar, meaning the good x bar, meaning like the good version of x is this, maybe with a plus or minus. So it becomes x bar plus or minus this, y minus 1, c. And then we can add the S inverse back in, and we're going to apply S to all these terms. So we get this. And then this is just W. And so W of this, subtract W of this. And so the YV part cancels out with, sorry. This is just Y. So the YV part cancels out with this YZ part. So we just get this is equal to W of X bar plus or minus X dot, YZ. So W of this knot diagram is equal to the linear combination of W of these two. So there's two diagrams here. There's X bar YZ, which means XYZ, but with X replaced by a good crossing. And there's this one. And both of these have at least as many crossings as this one, but it has one less bad thing, like has one less bad crossing. So we can keep doing this until we get rid of all the bad crossings. So what we're thinking of is we're kind of like going S inverse, doing one tiny baby step of P, and then going back. And we're kind of doing this. It's kind of not, but it's kind of like this. So then we can, so suppose now we've gotten rid of all the bad crossings, no more bad crossings. And now we are on to sweeping. Okay, so we do the same thing with sweeping, but there's a little more, it's a little more complicated maybe. So again, I'll just copy the first part because the first part here is, oh no, I won't, I'll just rewrite it. So again, let X, Y, Z be the knot. And this time let X, there's no bad crossing, so let X be the first real crossing on the double point tree. Then to compute W of X, Y, Z, we do the same thing. We break it up into these two pieces, minus W, Y, Z. And we look at this part by itself first. So this is, let's do it quickly, VP and then S inverse, so we get X, Y minus 1. And now we're going to do a sweep. So to do a sweep, if this is our X, this is going to become like this. So X is going to be replaced by 3 other crossings, and we'll just call it maybe X1, X2, X3. So any diagram that used to have X now has X1, X2, X3. So we're going to write it like X1, X2, X3. And there's a mildly subtle point here because I'm writing VP of this is VP of this. So I'm saying doing one step of P to this part is this, and then doing the rest of P is the same as doing one step and then starting P again from the beginning. And this is true because we're going to remake the first come first served tree again right after this step. Like, so this repeating number 1 is necessary so that we can actually write this is the same as just restart, like, so that sweeping and then doing the recipe is the same as sweeping and then starting P all over again. Okay, so then we do this, and then we can put the S inverse back in. So now we're applying S to this whole term. So we get x1 plus 1, x2 plus 1, x3 plus 1, y v dot, and then subtract this. So the whole final thing we get is this is equal to w of x1 plus 1, x2 plus 1, x3 plus 1, y z dot minus y z dot. And so it's convenient, these like y z dots cancel out with the 1. So the only terms have at least as many crossings as this term. So all terms still have greater than n crossings. But now we're one fewer real crossing on the double point tree. Or like we're one step closer to, finishing P. So then we do this enough times, and so we do this, and maybe the next step is back to 2, and we just keep doing whatever is appropriate and until we get to a good diagram, and then we'll get a linear combination of good diagrams that together have the same W value of the original and also have greater than n crossings, and so it will be 0, and so this one will be 0. Okay. So sorry, this last part is like kind of gross and kind of weird. But basically we're just finding a different good diagram that has the same W value as our original diagram and also has greater than crossings, so everything goes to 0. And so we are done now. And I say but because this was a proof, but it was kind of, for example, there were many choices to make, and some of it's unclear, which of these choices were kind of just to make our proof easier and which part of these choices were necessary for it to work. Like, for example, we make a first come first served tree, and maybe we can say that's important because it kind of made this step easier to, then it's just snipping. But, could we build a tree in a different way and still have it work? And then this rebuilding this tree every time after steps 2 and 3 seems a little bit ridiculous. Like, can we not do that and just sweep and change? Because that would be a lot nicer. And then there's, of course, a lot of places where we're choosing an order on things. Can we change the order? And lastly, what I would like to do is maybe find a more direct description of W, because I don't know, I don't like it right now. And so before yesterday, when I figured out I didn't understand Rikama's proof, that was before I thought we needed to repeat step 1. So I thought it would generalize nicely to tangles, and now which are just, like long knots, but with many long strands, then they're all kind of tangled together. Maybe there's something like this, I don't know. And right now I do not see why the proof doesn't work, especially if we just choose an ordering on, these strands and we do kind of the same thing. I don't see why it wouldn't work, but I also am not confident that it works, so I don't know. I also wrote knots here because it might seem like because long knots are just knots, that it should work for knots. Like, we should just be able to, we have a knot, we just cut it open, make it a long knot, do this, and do everything. But it's because long knot diagrams, I think, are not quite the same as knot diagrams, especially if we introduce a virtual crossing. I don't know. I don't really know how it works, so I'm not confident to say. So here's another question mark. And links, I guess, has all the problems of these, but more. But it would be nice to generalize to all these things. And so one of the reasons, if we get rid of step 1 and we only need to sweep, or if we could just build any tree, then we have an easier proof, and it would be easier to generalize to these random things. Okay, yeah, that's it. Yeah, thanks for listening. Are there any other questions?
So just a quick question about the long knot diagram not being equal to knot diagram. So initially you said long knots are equal to knot by, say, cutting them or joining them together. So wouldn't they have the same diagrams?
Yeah, I'm not sure about if we are just viewing the diagrams as the crossing information, but if we look at it as virtual long knots and virtual long knots and virtual knot diagrams, I think are not this. Virtual knots are not the same thing, because when we go from knots to long knots, we can cut at any point we want, because we can, if we have like this part A and we have a part B on the long knot, we can swap the order of the two by making B very small and sliding it through. And I think this doesn't work with the virtual, if there's virtual crossings like in A. But then I don't know if the virtual crossings are important for the diagram. I don't know, maybe someone else knows better about this. I just don't know.
So can I add my comment? So my biggest issue is not with generalizations and not with the confusions you mentioned, but the loveliest proofs are the ones where you convince yourself that every step was natural. Sorry, we talked about it already, but I want to say here, okay? So it's those proofs where you convince yourself that every step was natural, where you convince yourself that any reasonable person, or at least any reasonable person who has all the relevant background, would come up with that proof. Basically, at each step, you do the only thing possible, or if you don't do the only thing possible, then it doesn't matter what you've done. I mean, then the other choices would work too. But somehow, if you can describe the proof in a way that it feels like any idiot would have found it, and we're not there yet. So that's the main thing that bugs me. Yeah, sorry, that's just my comment. Somebody left, hasn't? Who?
I think Nancy had the meeting, so she had to go.
Oh, Nancy. Okay. Oh, but wait, so then what's happening with the recording? What's happening with, she was the boss. I mean, she's the only person not allowed to leave. Okay. We'll see. Any other comments?
Oh, I just wanted to ask again, could you remind me what the U was, the U and the V in front of the D's?
Oh, yeah. This is, I guess, George's notation. U for usual, meaning representing a usual knot, and V for virtual, yeah.
Looks like the kind of a universal, I don't know, property or something like that.
Say that again?
No, it has nothing to do with universal. It's just usual and virtual.
No, I mean the maps, the way the maps were constructed, and there exists a W. It looks like a universal property.
Well, they're like commutative diagrams, Well, so since Nancy left us, I'll take the role of the chair again instead. And so see you next week. And hopefully Leonard will be telling us about what he's doing. And let's thank Jessica once again before we go. So unmute your microphones and let's clap our hands. Okay.